Fine. So we are going to talk about geophysical investigations, which, thanks to experts, all of them who are sitting here, these are becoming popular at various investigation stages. But still, the full potential of geophysics is yet to be realized in most of the fields, including tunnel investigation. So as Dhawan Saab has already covered, first of all, it's very important to understand where do we fall when we talk about geophysical investigation. What's the sequence? So as he said, it's starting with available geological maps, satellite images, geological mapping, and after that comes geophysical investigation, right? And it always should be before drilling. And the idea is, again, as he very clearly said, rather than drilling just randomly, we should be looking at drilling at the right locations. And that is where geophysics comes in picture, when we can optimize the drilling and we can do it at the right location to get maximum possible information in a continuous way. Continuous is a key word here, because we all know drilling gives us discrete information. And unless we position our drill holes correctly and we do not get information of what's happening between the drill holes, we are missing a large part of the full picture. And then, of course, drilling with and other studies, and it's there. I'll just show you glimpses of 5 or 6 important methods and where do they fit in. First is Helibon time domain electromagnetic, as we talk about. As Dr. Dhawan showed a photograph of a project in Bhutan, where you saw the tunnel route with a red line and the entire thing was full of vegetation. There was practically hardly any outcrop to be seen. Even going at these places is very, very difficult in the initial stages of investigation. Drilling is very difficult in such places. And there are a number of options to go from point A to point B. Now, that's where this system is kind of it can change the way we look at it. We are working with a loop. It's an electromagnetic loop, which is being suspended from a helicopter. And then it is being run over the area. Is scanning not just one line from point A to B, but an area. So you can take a strip of 500 meters for the total tunnel length of 10 kilometers. So 10 kilometers by 500 meters, you are investigating the complete strip. And based on that, you are making kind of a 3D model of what you can expect in the subsurface. Now, this gives us information even when there is a thick vegetation, because we are using electromagnetic waves which are not affected by vegetation and trees, canopy, etc., etc. Depth of penetration with dual moment sensors can be as high as 700 to 800 meters today. So this is something which can be the starting point after your geological mapping to decide the right path of the tunnel, right? Because if point A to B, you have a lot of problems or bad zones coming in between, you can take it to a different path. So this is one. This is a kind of result which you get. So here you see the depth. It's around 700 meters from top to bottom. And wherever you are encountering, you can say the bad zones will be the one with very high conductivity. So these will be fracture zones or shear zones where you can expect a lot of issues by tunneling. These kind of zones can be quickly mapped using this. And this 3D model gives you a very good data to start planning your tunnel. Then is passive seismic tomography. The first one, this already has been used in India in a couple of projects. Passive seismic tomography is listening to micro earthquakes which are happening under the earth all the time. And ultimately, based on this, you are making a VP or VP upon VS model, which gives you structural and lithological information. Here, depth of investigation is not an issue at all. We have used tomography in Assam and Tripura areas up to a depth of around 15 to 20 kilometers. Okay, but this is yet to be applied in India in any project. Again, you get this kind of information. As you can see, the depth of investigation here is very, very high. So we are talking of more than 2 kilometers, around 2.4 kilometers depth of investigation. And these blue ones, for example, are the zones which are problematic zones because of their low P wave velocity. Then there are methods like seismic refraction tomography, which gives you a very good information on, for example, your thickness of soil, thickness of weathered layer, thickness of your depth to the bedrock in terms of P wave velocity. And you are able to see small shear zones or faults, etc. It can be done across water also. And so this is just an example of a tunnel project, because Dhawan Saab said I must include some case studies. So this particular tunnel project was done, and this model was developed based on geological study only and few drill holes. You can see few drill holes there. And along the tunnel route, there was no major surprises which were expected. But when seismic refraction tomography was conducted here, you can see this would have come as a geological surprise. This would have come as a geological surprise. This would have come as a geological surprise. But once investigated, we know when we are going to hit these zones, loose zones, weak zones, and now we can prepare for it and then treat these zones before we go ahead. Electrical resistivity imaging or electrical tomography is another very interesting technique, which again is very effective in detecting small shear zones, voids, etc. So something like this. This is an example of a tunnel in J&K where a shear zone was detected using ERI, electrical resistivity imaging. This again is a depth scale. This is distance. And the depth of investigation of ERI today can be as high as 300, 400 meters if it is required. All right. And this is another example of ERI for a tunnel project where this was a tunnel route, and here the fracture zone was detected. Here a zone was detected. And after that, drilling was done. So this is a inclined drill hole which was planned basically to investigate the nature of this zone. This is the right way of doing it, rather than just doing, let's say, drilling every 50 meters or 100 meters and completely missing out this zone by theory of probability. Once you know the zone, we can drill there and find out more about it. Then seismic or sonic tomography, again, is a very effective technique to interpolate between your boreholes, which you are anyway doing. But between boreholes, what's happening? So you have a borehole here, one here, and then in between we do tomography. And for example, this fault was detected based on the tomography between the boreholes. So very effective technique for even a higher resolution. This also can be done between drifts. We have done projects where you did drift, and then between the drift, we did the tomography to classify the entire medium between the drifts. Another example from a project where cavities were detected. Borehole were as deep as 250 meters, and distance between borehole at one point was as high as 115 meters. And this entire cavity was mapped, and based on that, of course, then filling was done to rehabilitate this area. Then last topic is QC of completed tunnels. Once your tunnel is completed, sometimes it has problems like seepage, etc., or you want to do a quality check. So this is the GPR being done for the quality check of the lining, and you can get defect zones or the zones with the problem or delamination or the void behind the lining, etc., very effectively using this. The 3D result. So this is the tunnel, and the lining has been scanned using a GPR, and you can see behind the lining what is the status of. So this is the bad zone. How it is continuing all over the tunnel is very clearly visible in this. Last slide, which I would like to show you, is same thing for ERI, electrical resistivity imaging. We did these electrodes are placed on the lining, and then the seepage was coming out from here, and it was desired to find out where is it coming from. And once this was done, it became clear that this was a saturated zone from where the water was finding this path to ultimately leak out here. Now, once you have this kind of insight, you can actually treat these zones and stop these kind of problems. Once the tunneling starts in challenging areas like cities, like Delhi, for example, by TBM especially, you want to find out what's happening ahead of a tunnel. If you are going to encounter an aquifer or a bad zone, even metallic objects. For that is a technology of beam, which is working on focused electrical method, where you can continuously see 3 times the diameter of tunnel ahead, what kind of strata is coming. Is it a cavity? Is it a bad strata in terms of any other anomaly? So ultimately, we use geophysics for rapid coverage and continuous information. It does not replace drilling. It optimizes drilling, minimizes the surprises, but it should be done at an early stage application, not as a firefighting tool. So Dhawan sir, thank you very much for giving me this opportunity to very quickly go through it. It was very quick, but I just think I could do some.
Thank you, Dr. Rana. Really, they say brevity is the soul of wit, and you have proved it, that in 7 minutes you have covered the entire range of geophysical methods. And I'm sure that our listeners will be greatly benefited with this. And as Dr. Rana said, that drilling has to start only after geophysics. I mean, because first of all, let us do engineering geological mapping, then update the model. Because, you know, the philosophy is engineering geological model will tell you something, some gray areas. Now focus on those gray areas with geophysical tools. Either geophysical methods will rule out those gray areas, or they will further add some dark shades to that. And that is the time to confirm that what these two surface methods or subsurface methods have given you. Then you have to apply drilling. And the main objective of drilling is to notice lithological variations, thickness of overburden, calibration of geophysical results, presence of water, that is water table, collection of samples for lab testing. Then these can be used for in situ testing also. Holes can be later on used for monitoring of inclinometer, piezometers, etc. Then degree of jointing fracturation, through which, you know, we calculate RQD, which is a very important parameter for assessment of the rock mass. And these are useful for providing precise information for geology and geotechnical setup. Here, you know, one aspect is that you have placed your boreholes based on geological and geophysical results. But another aspects are how to optimize it. In the figure above, this is, I have borrowed from my friend, Mr. Sumit Jain, RVNL. He used it in one of our presentations. With his permission, I normally use this figure, in which you will see that these are very steeply dipping beds and boreholes are vertically aligned. You will see that for going up to the tunnel grade, very long drill holes would be required. And every time you can't drill, I mean, maybe that some people may be thinking that am I suggesting putting a drill hole at the mountain top? No, these are just, you know, schematic locations, because you can't go to the mountain top every time. So in geology, you have to find out that from where I can intercept a lithological formation which I'm looking at. So you see, we have to consider geology before making the drilling program. And in the figure below, you will find that respecting the knowledge of geology, these boreholes are inclined oblique to the geological formations. So you will see that with shallower drill holes, we are able to collect more information about various lithologies. So every hole is not required to go to the tunnel grade. Some of the holes may go if it is so desired. Otherwise, we can, because our aim is to restrict our depth of drill holes around 200 or 250 meters, because in India, although technology is available, but in Himalayas and other hilly terrains, even in Peninsular India also, many times you can't take your bigger drill machines inside these areas. So therefore, you know, the drill holes are to be placed giving respect to geology and topography. Next is exploratory drifts. These are one side open test tunnels of 2.1 to 1.8 meter. But this is not a very well-defined standard. Depending upon your requirement, you can make bigger drifts also, but this is what we used to follow in hydropower sector. So these are very useful for determination of rock mass conditions, estimate depth of stripping, glide cracks, slump areas, and evaluating the tunneling condition and the support design. These are very useful for in situ rock mechanic testing, particularly, you know, shear parameters and rock stress parameters. This is a list of various kinds of rock mechanic testing which is required to be performed for understanding the engineering properties of the rock mass. As far as the lab tests are concerned, we collect the strength parameters and deformability parameters, UCS point load, Brazilian test, modulus of elasticity, Poisson ratio, triaxial strength, slake durability, and physical properties. As far as in situ tests are concerned, we can use these tests for finding out in situ deformability, shear parameters, in situ stresses, bearing capacity, and liquefaction. There are several methods which are listed down. So just to have a recap, whatever we have spoken till now, or whatever philosophy I have presented to you today, we start with the PFR stage, which is a geological appraisal stage, and we have these inputs handy with us, ranging from the topographical surveys to regional geology, stratigraphy, seismotectonic studies, preliminary site visit, and geological maps and sections, whatever are available. These all are desk studies, whatever are available to us or at our command from literature. At that stage, we do a kind of ranking study and select not the final, but some of the preferred alternatives and go for the next stage. And the next stage is identification of the risk areas and avoid that, as Dr. Rana said, and then plan for the feasibility stage investigations. This is the whole cycle in which PFR I have explained, and then we go to the feasibility stage studies, wherein we focus more on engineering geological mapping and try to come out with a model. I will show you a sample from RVNL on 1:25,000 scale, and we should give at least 6 months time to these studies to really do a good job. And then we go to preliminary design stage, wherein we update. First of all, here we start with geophysics, then we update our geological model, we update our engineering geological map. From 1:25,000, we go to 5,000 and have a bigger map with us with more details, better mappable units. And in the third stage, we go for geotechnical investigations, drilling, drifting, rock mechanic testing, and other special tests which may be required depending upon the requirement of geology as far as the project. And now at this stage, we should have enough data to synthesize a GDR, the Geotechnical Data Report, and the DPR. This is the conventional document in India which is required for seeking approval of the regulators. And in the last stage of investigations, once we receive all approvals and all balance investigations are done, then we go for GIR and geological baseline report, which will be required for tendering process. So these are few samples. I mean, why this topic occurred to me, because we are, if not monitoring, we are in touch with whatever is happening at RVNL project at Rishikesh. So I found that they have done a very systematic investigation. I have seen their reports, and the results of investigations are now giving them very rich dividends, and you will appreciate the kind of progress they are giving at their DBM phases as well as TBM phases also. Touch wood, they are doing a good job, and we wish that this project should complete without any problem. So this is their geological reference model, they call, of 1:25,000 scale, wherein they have modeled the geology and only on the basis of lithology. And I think all the geologists will appreciate it very much, and my engineer colleagues will also appreciate it, wherein you can say that due to a synclinal, Garhwal syncline, these units are getting repeated. In the next stage, which was the third stage, now the geology is updated on a bigger scale, and all these parameters are plotted. Particularly, we start from geology, and then several trouble areas are recorded. These are faults, water inflow, bedrock type, and Nala crossings, river crossings, and they have numbered them as from A1 to A9. This is in geology. And then geomechanics, the UCS and GSI. And then in the bottom, they have given the instability modes, whatever kind of instability may occur. And why I am presenting this section to you, that the most important thing is they have conducted a geological reliability model through this. And you will see that there is a small index which is not readable for you, but for your benefit, I will tell you that this green is the best fit, then the intermediate and the low reliability. The red is low reliability, and this is here along this line. So this is the medium reliability. Now, in entire section, if we do that, we will come to know that what are the areas where we need to focus more in the next stage. And in the next stage, then along with the rock mass classifications, we may give a table in which for every sector with the chainage, we can say that what are the critical elements or what are the main geological hazards which are expected. And this becomes finally the basics of the risk analysis. So with this information in hand, we can go for a very good risk analysis for all sectors of the tunnel. And this is the final outcome if you do a good geological assessment of your tunnel. In other words, if you know your ground type well, you will have a better data to select the excavation method. And if you can do a good excavation, you will go for right kind of selection of supports. For example, in a strong rock, you have option of go for drilling and blasting or TBM or road header. You can go for anything, and some minimal supports are required. But for the fair rock, if whatever sectors are there and the rock is not very good, it's weak, then even then you can go for full phase depending upon the size of the tunnel, the diameter, and then you will have an idea that let's go for open shale tunnel. In squeezing rock, then you will have to go for heading benching, or if the rock is still poorer, you will have to go for multi-drifting, and you can choose double shale TBM or EPB closed phase TBM. And accordingly, the support system will also be. These are the broad just depiction of the, I mean, this kind of outcome can be expected if good investigations are done. Here, this red area where the investigation heading is given, and then the blue one, you will have a better planning and construction program, and you can design in a better way. So this is the final outcome of the investigations which we may be doing. And in my personal opinion, synergy has to be is a must between geologist and engineer. A geologist must provide the required information to the designer and engineer, and engineer must understand the limitation of geologists and provide for additional treatment and safety measures in design as well as in tender documents. And this is my friend Yogendra Deva and myself in Chamera Dam during the last training program of EGM in last June. Thank you very much. So